Right now, a veil of particles smaller than smoke is controlling the climate of a world billions of miles away. That world is ancient, frozen, and smaller than Earth's moon. Its atmosphere is so thin that, as its orbit carries it farther from the sun, much of the air may eventually freeze onto the ground. Yet that fragile atmosphere is doing something scientists had never directly observed anywhere else in the solar system. And the James Webb Space Telescope has finally measured it. The discovery came from heat that should have been almost impossible to isolate. Pluto was far beyond Neptune. Its largest moon, Charon, appeared beside it. Both were tiny points in Webb's view, separated by less than the apparent width of a small coin seen many miles away. Previous infrared telescopes often blended their warmth together. Webb pulled the signals apart. But here is the part that changes this from an impressive measurement into a planetary mystery. The unexpected heat did not come mainly from Pluto's surface. It came from the haze suspended above it, a blue, layered smog that appears to cool the atmosphere by radiating energy into space. For years, that idea sounded almost too strange to be true. Now Webb has seen the predicted signature, and buried inside the same data are other surprises. Fluorescent methane, unexpected chemical abundances, icy particles, and a clue about where Pluto's material may have originated. To understand why any of this matters, we have to return to the beginning, when Pluto was not a world with glaciers, weather, and an active climate. It was barely a moving dot. In 1930, Clyde Tombaugh discovered Pluto by comparing photographs of the night sky and searching for a point that changed position. For decades afterward, even powerful telescopes could reveal little more than variations in brightness. Pluto is distant, faint, and frustratingly small. Its average distance from the Sun is a roughly 5.9 billion kilometers. Sunlight takes about 5.5 hours to reach it. At local noon, the Sun would look like an intensely bright star, but its illumination would be only a tiny fraction of what reaches Earth. That distance shaped the old picture of Pluto. It seemed reasonable to imagine a frozen relic, preserved in darkness, geologically exhausted, and almost featureless. Then astronomers found Charon. Charon is so large compared with Pluto that the two bodies orbit a point in empty space between them. 4 smaller moons circle the pair, creating a compact system at the inner edge of the Kuiper Belt, the broad population of icy objects beyond Neptune. Even then, the central assumption survived. Pluto might be historically important, but it was probably simple. New Horizons was built to test that assumption. Launched in 2006, the spacecraft crossed the solar system for more than 9 years. Its assignment was modest in one important sense. It would not enter orbit. It would race past Pluto once, gathering everything it could during a brief encounter, then continue into the Kuiper Belt. There would be no second attempt. The navigation had to place a small spacecraft inside a narrow corridor after a journey of billions of kilometers. The science sequence had to work largely on its own because a command from Earth took hours to arrive. During the most valuable observations, the antenna would point away from home and toward Pluto. Mission control would be waiting in silence. Just days before the encounter, that silence nearly became permanent. The spacecraft lost contact and entered a protective safe mode. Its main computer had become overloaded while preparing commands and compressing science data at the same time. On Earth, engineers worked against a deadline that orbital mechanics would not move. Pluto was approaching. The spacecraft was approaching. Every hour lost meant observations that could never be repeated. The team restored control and rebuilt the command sequence. New Horizons returned to science operations before the flyby. Then, on July 14, 2015, it passed about 12,500 kilometers above Pluto's surface. The expected frozen relic disappeared. New Horizons found mountains made of water ice, some rising several kilometers. It found enormous sheets of nitrogen ice behaving like glaciers. It found plains with so few impact craters that parts of the surface appeared geologically young. Most recognizable was a bright, heart-shaped region. Its western lobe, Sputnik Planitia, is a vast basin filled with mobile nitrogen ice. Slow convection appears to renew sections of that plain, bringing warmer material upward as cooler material sinks. Think about what that means. On Pluto, water ice forms the bedrock in mountains because it is rigid at such low temperatures. Nitrogen ice can move more like soft ice on Earth. The familiar roles of rock and glacier have been reassigned, and then came the atmosphere. After closest approach, New Horizons looked backward as Pluto passed in front of the Sun. Sunlight outlined a delicate blue ring and revealed layer after layer of haze rising more than 100 kilometers above the surface. The haze was not merely higher than expected. Pluto's upper atmosphere was also dramatically colder than standard models had predicted. Those models treated gas molecules as the main agents that absorb and release energy. Under that framework, the atmosphere should have remained warmer. The measurement contradicted the accepted picture. A colder atmosphere is more compact. Its molecules move more slowly, and fewer can escape Pluto's weak gravity. New Horizons, therefore, found atmospheric loss far below some earlier predictions. The haze, the cold temperature, and the low escape rate seemed connected, but the mechanism was missing. This is where the story changes. In 2017, researchers proposed that Pluto's haze might not be a passive decoration. It might dominate the atmosphere's entire energy balance. The idea begins with methane and nitrogen. Ultraviolet sunlight breaks these molecules apart high above Pluto. Their fragments recombine into hydrocarbons and more complicated organic compounds. The material gathers into particles, becomes coated with condensed ices, and slowly falls toward the surface. In visible light, those particles scatter sunlight and create Pluto's blue atmospheric rim. Over long periods, their chemistry also helps produce the reddish material spread across parts of the ground. But the model proposed another role. Haze particles could absorb energy from sunlight and surrounding gas, then release that energy efficiently as mid-infrared radiation. Mid-infrared means wavelengths longer than human eyes can see, where cool objects and fine particles reveal their thermal glow. If the particles radiated enough energy into space, they could refrigerate the surrounding atmosphere. The same smog that absorbed energy could also become the planet's dominant cooling system. That explanation solved one mystery, but created a test. If the model was right, Pluto should glow more strongly in the mid-infrared than its surface temperature alone could explain. At the time, no available telescope had the sensitivity needed to make a clean measurement. The prediction had to wait. James Webb was designed mainly to study the first galaxies, newborn stars, and atmospheres of planets orbiting other suns. Yet its position in space, enormous mirror, and infrared instruments also make it unusually capable of studying faint objects in our own solar system. To measure such faint heat, Webb must first hide its own. Every warm object emits infrared radiation, including a telescope. If Webb faced the sun without protection, its own glow would overwhelm the distant signals it was built to detect. A 5-layer sunshield, therefore, keeps the mirror and instruments in permanent shade while the warm spacecraft systems remain on the other side. Even that is not cold enough for the mid-infrared instrument, known as MIRI. Its detectors operate below 7 kelvins, less than 7 degrees above absolute zero. A dedicated refrigerator circulates helium through the observatory to carry heat away. Before science operations began, engineers had to guide that system through a difficult cooling transition called the pinch point. The refrigerator's ability to remove heat briefly reached its weakest stage just when the detectors needed to become colder. Valves and compressors had to be adjusted in careful sequence. If the cooling became unstable, the instrument designed to reveal the cold universe would be blinded by its own warmth. The procedure worked. That engineering is easy to forget when a finished spectrum appears as a clean line on a screen. Yet every rise and dip in Pluto's data depended on a machine keeping itself colder than the world it was observing, while operating about 1.5 million kilometers from Earth. Webb could not be repaired by a waiting crew. The telescope, its shield, its refrigerator, and its detectors all had to remain stable enough to distinguish the heat of atmospheric dust at the frontier of the solar system. Pluto presents a peculiar challenge. Webb is powerful enough to detect it easily, but Pluto and Charon sit extremely close together in the sky. Their thermal signals overlap. The telescope must also track their movement against distant stars while maintaining exquisite stability. This is the sense in which the observation seemed almost impossible, not because physics forbade Webb from seeing Pluto, and not because Pluto had never been imaged before. The challenge was to separate two tiny cold worlds at a distance of billions of kilometers, then measure small changes in their heat as they rotated. In October of 2022, Webb observed the Pluto and Charon system 6 times across one complete mutual orbit, lasting about 6.4 Earth days. The visits sampled different longitudes, allowing researchers to build separate thermal light curves. A thermal light curve records how infrared brightness changes as an object turns. Brightness rises when warmer or more emissive terrain faces the telescope. It falls when cooler terrain rotates into view. Webb measured the pair at wavelengths near 15, 18, 21, and 25 micrometers. A micrometer is 1/millionth of a meter. At these wavelengths, the telescope is not simply photographing reflected sunlight. It is measuring heat and the way materials emit that heat. There was still a problem. The apparent separation between Pluto and Charon was comparable to the width of Webb's own blurred point of light at those wavelengths. Their images overlapped. Researchers modeled the shape of each point and disentangled the two signals. For the first time, they recovered Charon's individual thermal light curve while also obtaining cleaner measurements of Pluto. Tiny changes became a map without a picture. Charon's signal exposed differences between its bright water ice terrain and its darker polar material. Pluto's curve reflected a more complicated mixture of methane ice, water ice, dark deposits, and volatile terrain that exchanges material with the atmosphere. But surface models alone could not reproduce all of Pluto's infrared brightness. Something above the surface was glowing. The researchers added atmospheric haze to their models. The fit improved, and the extra emission matched the central prediction made years earlier. Webb had detected the haze releasing thermal energy. This was not just another ingredient in a model. The measured flux indicated that haze strongly influences, and may largely control, Pluto's atmospheric heat balance. Without that haze effect, models placed the upper atmosphere near minus 173 degrees Celsius. With haze cooling, the temperature can fall near minus 203 degrees Celsius. 30 degrees is a vast difference for a tenuous atmosphere. It changes circulation, chemistry, pressure, and the rate at which molecules escape. It may also change how volatile ices migrate across the surface as Pluto moves through its long seasons. Now the story gets stranger. Earth has aerosols, meaning small particles suspended in air. They influence climate. Titan, Saturn's largest moon, has a thick orange haze with major effects on its atmosphere, but the Webb results indicate that Pluto may be the clearest known case where haze particles dominate atmospheric cooling on a global scale. This is a new kind of climate regime. The gas is not doing most of the thermal work. The particles are, and those particles are complicated. The best interpretation includes organic material resembling Titan's haze, mixed with frozen hydrocarbons and nitriles. Nitriles are compounds containing carbon and nitrogen. In Pluto's cold atmosphere, chemistry can become weather, and weather can settle onto the landscape. Pluto's climate therefore connects sunlight, gas, haze, frost, and terrain in a continuous cycle. Weak ultraviolet radiation begins reactions high in the atmosphere. Nanometer-scale particles grow and fall. They cool the air while carrying material downward. Some eventually darken the surface, which changes how sunlight is absorbed, which can influence temperature again. Tiny particles reshape an entire world. The thermal light curves were only part of Webb's investigation. In May of 2023, its mid-infrared spectrometer spread Pluto's light into a spectrum from roughly 5 to 27 micrometers. A spectrum separates light by wavelength. Molecules leave characteristic peaks or dips, allowing researchers to identify substances that cannot be seen in an ordinary image. Webb clearly detected several products of methane chemistry, including ethane, acetylene, propyne, and diacetylene. These molecules act like tracers through Pluto's atmospheric reaction network. Some results agreed with chemical models, others did not. The measured amount of propyne was about 10 times lower than predicted. Diacetylene was about 5 times lower. Acetylene did not fit the expected pattern cleanly, suggesting that its vertical distribution, or its method of emitting light, needs a better explanation. Accepted chemistry met a new measurement, and the measurement refused to cooperate. Then Webb detected methane behaving in a surprising way. Some methane and deuterated methane molecules were fluorescing. They had absorbed solar energy and re-emitted it through a non-thermal process, rather than glowing simply because of the local temperature. Their vibrational excitation appeared more than 20 degrees warmer than the surrounding gas. That behavior resembles processes observed in cometary atmospheres. Pluto is not a comet, but its thin air, weak collisions, volatile ices, and distant sunlight can produce chemistry that crosses familiar planetary categories. Webb also detected a form of acetylene containing deuterium. Deuterium is a heavier version of hydrogen with an extra neutron in its nucleus. The ratio between deuterium and ordinary hydrogen can preserve information about the formation and evolution of ancient ices. The measured ratio was roughly 3 times the terrestrial value, although the uncertainty remains significant and its interpretation is not settled. That is another open door, not a final answer. Different regions of the early solar system developed different chemical fingerprints. If researchers can compare Pluto's deuterium ratio across gases and surface ices, they may learn whether its material formed where Pluto is now, migrated from elsewhere, or changed through billions of years of atmospheric loss and seasonal recycling. The smallest spectral feature can become a record of planetary ancestry. But there is a crucial limit to what Webb has done. It has not resolved Pluto's mountains and glaciers the way New Horizons did. Webb's strength is different. New Horizons delivered an extraordinary close snapshot from one brief encounter. Webb can return to the system, measure infrared wavelengths the spacecraft could not cover, and watch the climate evolve over time. One mission supplied detail. The other supplies duration. That matters because Pluto is changing. Its orbit around the Sun lasts about 248 Earth years and is noticeably elongated. As its distance and seasons change, surface nitrogen, methane, and carbon monoxide can sublimate into gas or condense as frost. Sublimation means changing directly from solid to gas. On Pluto, it can move enormous amounts of material without ever forming liquid. Scientists still do not know exactly how the atmosphere will respond as Pluto recedes from the Sun. It may decline gradually. Large portions may eventually condense onto the surface. Haze production may weaken as methane availability and sunlight change. Different regions may exchange frost in ways current models do not capture. The Webb measurements provide a new baseline during that transformation. Right now, teams can combine the mid-infrared data with Webb's near-infrared observations, ground-based stellar occultations, and the New Horizons archive. A stellar occultation occurs when Pluto passes in front of a distant star, allowing the dimming starlight to probe the atmosphere. Each technique sees a different layer of the same system. Together, they can test whether haze cooling changes with season, whether the chemical contradictions persist, and whether Pluto's atmosphere is beginning a long retreat toward the surface. This is why the first Webb observations are not the ending. They are the opening measurement in a climate record that could outlast the careers of the people who began it. There is also a larger implication. Pluto is a natural laboratory for hazy, nitrogen-rich atmospheres. Titan belongs to that family. Neptune's moon Triton may belong to it. Early Earth may have passed through chemically hazy states. Some distant exoplanets may be wrapped in particles that control their temperatures more strongly than gases do. If astronomers interpret those worlds using gas alone, they may misunderstand what their telescopes are telling them. A faint thermal excess from Pluto can therefore improve the way we read planets around other stars. The distant becomes relevant, the tiny becomes consequential. If you want to follow that unfolding record, subscribe before Webb returns to Pluto's changing atmosphere. Not because one observation has answered everything, but because it has revealed exactly which questions were hiding in the haze. Pluto was once treated as the last simple world at the edge of the known solar system. New Horizons showed that its surface moves. Webb has now shown that its haze may govern the sky. And at this exact moment, beneath a sun that looks like a brilliant star, microscopic particles are still falling through blue twilight. Still glowing, still cooling, still writing the climate of Pluto into the dark.